Thank you so much. Yeah, it's a real pleasure to be here. And I know there's another talk here at 1, right? So I guess I'll get right into it. Yeah, I'm going to be talking about some work I've done relating to El Niño teleconnection patterns. I'd like to acknowledge Yu Kosaka, who's a collaborator on this project, and I've also had a number of stimulating conversations with Stephen Feldstein, Changping Xie, Suk-Young Lee, Michelle LaRue on subjects related to this topic. So I just wanted to acknowledge them. Okay, just to give some background on ENSO. So the El Niño-Southern Oscillation, or ENSO, I would say it's the dominant source of seasonal predictability over North America. So when we have an El Niño, we have above average sea surface temperatures in the equatorial tropical Pacific. If we have the opposite phase, it's called La Niña, and it's a similar pattern but opposite in sign. So like what we're seeing right now, we have negative SST anomalies in the equatorial eastern Pacific. And ENSO has a very broad impacts. So here I'm showing a schematic that has the typical El Niño impacts during boreal winter. You can see during El Niño we tend to have above average temperatures over northwestern North America. It tends to be cool and wet over the southern U.S. But we see impacts over virtually every continent: South America, Australia, Southeast Asia, Africa, etc. So very large-scale impacts. So ENSO is quasi-periodic. We'll typically have El Niño once every 2 to 8 years. We have some predictability for ENSO out to lead times of several months to around a year. And both ENSO and its northern hemisphere teleconnections are strongest in winter. And I'm going to be focusing on boreal winter in this talk. And typically we monitor ENSO by SST anomalies in the so-called Niño 3.4 region. That's this region outlined in this black box. And the NOAA Climate Prediction Center defines an El Niño when the Niño 3.4 SST anomalies exceed 0.5 degrees Celsius for 5 consecutive overlapping seasons. And if you go to the NOAA CPC website, you can look at the historical record of past La Niña and El Niño events. And here I'm just pulling out the last about 7 to 8 years. Showing the Niño 3.4 SST anomalies, and then the red is corresponding to El Niño winters, or El Niño seasons, and blue is La Niña seasons. So you can see our last 2 El Niño winters were the 2014-2015, which was a weak El Niño, and then we had the mega El Niño 2015-2016. And then we transitioned into a weak La Niña last winter, though weakened by midwinter. We had some rebound, and now we're heading back down and expecting a weak to moderate La Niña for this rest of this winter. Okay, and so just to drive home this point of how ENSO is such a strong force in our seasonal predictions, here I'm pulling up the NOAA 2018 winter outlook for precipitation and temperature, and these are plots I pulled from the climate.gov ENSO blog, and I just thought I'd plug this since I'm one of the bloggers now on this site. So we have 2 posts per month talking about monitoring ENSO and other ENSO related research. So it's written in very plain language. So target audience is not a scientific audience, but just the general public. So it's I think a neat way to connect the prediction and the research to the general public. So anyway, so this shows that for this winter outlook, NOAA's calling for above average probabilities of precipitation being above average over the northern U.S., below average over the southern U.S., enhanced probabilities of above average temperature over the southern and eastern U.S., maybe cooler over the Pacific Northwest. Not a real strong signal over Stony Brook, just slightly enhanced probabilities of above average temperatures. But you can see that this forecast, though, it really does match sort of the canonical La Niña impacts. So it's showing that this La Niña is a real important factor in these outlooks. Now that doesn't mean that these patterns are actually going to verify. There are other important factors. They're just generally tougher to predict on seasonal timescales. Okay. So El Niño impacts remote weather and climate by exciting these so-called atmospheric teleconnection patterns. So when we have an El Niño, we have again above average sea surface temperatures in the equatorial eastern Pacific, And we tend to have enhanced deep convection in the central equatorial Pacific. And this enhanced convection can excite these poleward propagating wave train type patterns that modify the storm tracks, modify heat and momentum transport, and impact the climate anomalies over downstream regions like North America. And if you look at the composite 300 millibar height anomalies for El Nino, you can see it resembles this schematic fairly well. So during El Nino, we tend to have a stronger than normal Aleutian low, below average heights over southeastern U.S., above average heights over Canada. And in terms of the canonical teleconnection patterns, this pattern is sort of a blend of the positive phase of the Pacific North American or PNA pattern. So in the PNA, we tend to have positive PNA, we have a stronger Aleutian low, above average heights over Western North America, below average over the Southeast. It also has elements of the negative phase of the tropical Northern Hemisphere, or TNH pattern. So in the negative phase, this Aleutian low is strengthened and shifted eastward. We have positive anomalies over the Canada and negative anomalies over from Florida extending into the Atlantic. So this composite pattern has a blend of these kind of features. So that was the composite pattern. But if we look at individual El Nino events, we see that the wintertime anomalies can vary considerably. And here I'm just pulling up two different events that were classified as El Nino, the winter of 1988 and the winter of 1992. And looking at the 300 millibar heights, 2 meter temperature, precipitation, you can see the anomalies were quite distinct. So in over geopotential height, we could see almost opposite signs over large parts of North America. 2 meter temperature, 1988 much colder over the U.S., 1992 milder over the eastern U.S. Precipitation also very different, much wetter over the southern North America in 1992, and much drier in 1988. Okay, so the question is, why do the climate anomalies vary so much among different El Nino events? And there are a number of ideas that have been put out there, and the first one that I think is important to really consider is the role of atmospheric internal variability. So basically just weather noise. And although the time scale of atmospheric variations is short, generally on the order of 10 days or less, they still can leave a substantial imprint on the seasonal mean anomalies. And this idea brought out in these studies by Horling and Kumar and Horling, 1997. And and it's brought out in this figure. I know it's hard to see, but they show 500 millibar height anomalies for 4 different El Nino episodes. And it's hard to see the details, but the main idea is that they're very different. However, if you look at climate model simulations, so-called AMIP-type simulations that are forced by the underlying SSTs, so these are simulations that are attempting to isolate the SST-forced atmospheric response, you can see there's much less variation in the response. So their argument is that the SST force response is similar among these episodes, but these differences can be attributed to basically this weather noise, this atmospheric internal variability. But there are limitations to studies like these. For one, it relies on a GCM to capture El Nino teleconnections and their SST forced variations. And our climate models are not perfect, so they certainly may have errors in terms of being able to simulate these variations. Another idea that's gotten lots of attention in recent years are these so-called different El Nino flavors, with a particular focus on the difference between the Eastern Pacific and Central Pacific El Nino. And as the name implies, the Eastern Pacific El Nino is centered more towards the Eastern Pacific, Central Pacific more towards the dateline. And there are studies arguing that the impacts of Eastern Pacific and Central Pacific El Nino are distinct. For example, this Yu et al. Study suggests that for Eastern Pacific El Nino, it tends to be warm over northeastern U.S., cool over the southwestern U.S. But this pattern tends to be rotated about 90 degrees for the Central Pacific El Nino, so cool over the southeast, warm over the northwest. There are some limitations for these studies as well. So first of all, there's no single way to define Eastern Pacific versus Central Pacific El Nino. In reality, there's really a continuum of EP-like and CP-like patterns. So how do you partition is up for debate, and these differences are sensitive to exactly how we partition Eastern Pacific versus Central Pacific. And the other issue is that when we're partitioning historical events over the last 60, 70 years, we have small sample sizes, and we find that most of these observed differences are not statistically significant. Okay, and then the third idea I just want to bring out that was recently proposed by Chiotti and Harrison, that the key factor is the presence or absence of deep convection in the Eastern Pacific. And so they've categorized all the El Nino episodes in the satellite era, so since 1979, and they termed only the El Ninos that have deep convection in the Eastern Pacific as OLR El Ninos. And so you can see in the record there are 4 such OLR El Ninos. And they argue that only OLR El Ninos produce significant impacts over the US. So if you look at 500 millibar height, precipitation, temperature, you see statistically significant impacts for these OLR El Ninos, but the impacts for the non-OLR El Ninos are not significant. So this study also has a limitation, is that we're only limited by OLR availability to 9 total events, including 5 low amplitude non-OLR events. So these non-OLR events are lower amplitude, and since we have such a small sample size, and we're not expecting the signal-to-noise ratio to be that strong anyway, this may be just simply a reflection of the fact that we don't have enough samples to detect significant differences. Okay, but one thing I really do like about this study is that it gets into the patterns of tropical convection. So if there are predictable variations of the El Nino teleconnection patterns, it's likely going to be related to these patterns of tropical convection. So how do the patterns of tropical convection vary among El Nino episodes? Well, here I'm showing composites of the OLR anomalies for those 2 El Nino events I showed earlier. So this is 1988 on the left, 1992 on the right. So the 1988 event, you can see quite distinct. The negative OLR anomalies, so the anomalous deep convection, confined more towards the date line and actually have positive anomalies to the east. Whereas 1992, which was a stronger event, had negative OLR anomalies extending farther to the east. So this would be an OLR El Nino, the Chiotti and Harrison terminology. So the question, why do we see such distinct OLR patterns? Well, let's first focus on the central equatorial Pacific box right here. And what I'm showing here is on the y-axis, these are OLR values, and then on the x-axis, it's the relative SST in this box. And by relative SST, I mean the local minus the tropical mean. And I'll explain my motivation for using relative SST in a minute. But what you can see is in this box, the relationship between OLR and relative SST is pretty linear. So statistically speaking, we're not going to be able to do much better than just fitting a line. Now let's focus on this eastern equatorial Pacific box. And we can see that the relationship is very different. So there's very little change in OLR until we hit a threshold, and then a rapid increase. So for this region, we're better off fitting a line above a threshold. So we see 2 regions with very different relationships with OLR. And so why do we see such distinct relationships? Well, differences in the mean conditional instability of these 2 regions. So here I'm illustrating this by calculating the saturation equivalent potential temperature in the deep tropics from 20 south to 20 north, sorted by climatological SST on the x-axis and pressure on the y-axis. And the first thing you notice is that theta ES does not vary very much in the free troposphere. So in the deep tropics, temperature gradients are constrained to be weak. So we don't see a whole lot of variation. But we do see much more variation in the boundary layer. And you'll notice that below an SST of about 27.5 degrees Celsius, you can see theta ES increases with height above the boundary layer. So that means the atmosphere is stable, so not conducive for deep convection. But once you get above about 27.5 degrees Celsius, there's a deep layer where theta ES decreases with height. So it's conditionally unstable. We have mean CAPE. And you can see the Eastern Pacific climatological SST is climatologically much colder than the Central Pacific. So you can see if you increase SST, to 27, 27.2, it's still stable. So it's still not conducive to deep convection until we cross this threshold. And it's only after we cross this threshold that additional SST perturbations can help reduce perturbations in mean CAPE and deep convection. Whereas in the Central Pacific box, you can see it's conditionally unstable in climatology, so both positive and negative perturbations in SST associated with perturbations in the mean Cape and deep convection. So, so it really relates to the differences in the climatological SSTs. Okay. But this convective threshold, it's not a static quantity, and instead it closely follows the tropical mean SST. So this is work that I've done about 7 years ago now. That's showing how a measure of the convective threshold varies in both observations on the left and climate models. These are CMIP-3 models on the right. And you can see in both observations and models that the convective threshold closely follows the tropical mean SST. And the reason for that is because as the tropical mean SST increases, the upper tropospheric temperature also increases. That means theta ES is increasing. And so that barrier for deep convection is going to increase. And, and in the deep tropics, the upper tropospheric temperature changes in a very predictable way following moist adiabatic lapse rate adjustment. And, and as I showed in the previous slide, there's very little variation in free tropospheric temperature in the deep tropics. So there's a very small number of degrees of freedom. So that's why it can closely follow, the free tropospheric temperature can closely follow a single quantity like the tropical mean SST so well. And so that motivates the use of the relative SST rather than absolute SST. So the convection and relative SST relationships are more stable than convection and absolute SST relationships. And so this might not be too important if you're just looking at data over a period of a few decades, but if you're looking over longer periods when changes in tropical mean SST can be important relative to the interannual variability of Eastern Pacific SST, then I think using relative SST can be more useful. Okay. So then this leads to my just hypothesis that the most fundamental differences between predictable PNA region El Niño teleconnection flavors relate to this nonlinearity of Eastern Pacific convection with respect to relative SST. And so what I did is I simply just partitioned all the El Niño events since 1951, or between 1951 and 2014, into convective Eastern Pacific events and non-convective Eastern Pacific events. And that's just based on this relative SST criterion for this Eastern Pacific box. So if it's above this threshold of about 0.8 degrees Celsius, it's a convective Eastern Pacific event. Otherwise, it's non-convective Eastern Pacific event. So it's similar to the Chiotti and Harrison OLR El Niño criterion, except this has the advantage of having a relative SST criterion. So we can go back further in the record. And also, relative SST is something that's potentially predictable, whereas OLR is not, at least not directly on the seasonal timescales. Okay, so we do this partitioning, and we get 8 convective Eastern Pacific events and 13 non-convective Eastern Pacific El Niño events. And you might wonder, is this really any different from Eastern Pacific versus Central Pacific El Niño? Well, if we use the U et al. 2012 consensus categories, you can see that there is some overlap between Eastern Pacific and convective Eastern Pacific, Central Pacific, non-convective Eastern Pacific, but they're not the same thing. So I'd say no, it's not identical to just EP versus CP El Niño. Okay, so now let's take a look at differences in the SST and the OLR patterns between these two categories. So SST is in the color shading, OLR is in the contours. So this is December through March, and these anomalies are detrended. And in all cases, the composites are normalized by the mean Niño 3.4 SST anomaly amplitude. So I'm normalizing these composites because I want just to focus on differences in the pattern rather than the amplitude. And we know that the convective Eastern Pacific events tend to have higher amplitude. But if we look at the SST pattern, we can see they're not dramatically different, although the non-convective Eastern Pacific events tend to be shifted about 30 degrees to the west. The OLR patterns, however, are dramatically different. So you can see for, as we'd expect, for the convective Eastern Pacific events, the negative OLR anomalies extend all the way east towards the South American coast, whereas for the non-convective Eastern Pacific events, they're more confined to the dateline region. Okay. So now the question, are the teleconnection patterns distinct? So here we're looking at now at normalized composites of the 300 millibar height anomalies. So on the top left here, this is the convective Eastern Pacific. On the top right, the non-convective Eastern Pacific, and then here's the difference. And stippling indicates statistical significance of the 5% level. So you can see there are some notable differences between the two. And if we look at the differences, there are large regions over North America where the differences are statistically significant, particularly over northeastern North America and over southern North America. And if we just did the partitioning, Eastern Pacific versus Central Pacific, we find that actually the differences over North America are not statistically significant, and even though the same exact sample sizes between this partitioning. So this would suggest that this convective versus non-convective Eastern Pacific events, it's more fundamental from a teleconnection perspective in terms of differences over North America than Eastern Pacific versus Central Pacific. And that's not to say Eastern Pacific versus Central Pacific isn't important. I'm sure if we had higher sample sizes, we'd see more robust differences. But just I'm arguing that from a teleconnection perspective, this is more fundamental. And you go back to the two cases I showed earlier, the 1992 and 1988, you could see, okay, 1992 was a convective Eastern Pacific event, so it fits this composite better, and the non-convective event fits this composite fairly well. So suggesting that perhaps some of these differences that we saw these two winters, not just atmospheric noise, it also, there may be some predictable differences between the two. Okay, so with the observational record, however, we are limited in our sample sizes, so that's one drawback. So a lot of these differences are not statistically significant as a result. So it's helpful if we can supplement our analysis with these so-called AMIP-type simulations. And if we use a large ensemble and take the ensemble mean, that the large ensemble can help us to sort of beat down the noise of atmospheric variability. And so here I'm showing results from the GFDL AM2.1 forced by the observed time-varying SSTs from 1950 to 2012. External forcing is held constant 1990 values. And we're using 40 ensemble members, so it's a fairly large ensemble to really help to isolate the SST-forced signal when we take the ensemble mean. So here I'm just showing the convective versus non-convective Eastern Pacific events, again in observations, what I showed in the previous slide. And on the right is in the AM2.1. And you can see there are differences, most notably these differences over northeastern North America are much weaker in the AM2.1 than in observations. But there is some similarity in the pattern, so it's suggesting that the model is able to detect some significant differences between these two El Nino types. And I also want to take a look at the ratio, the inter-El Nino ensemble mean variance. So this is variance in the SST-forced signal only for El Nino episodes, and compare that to the within ensemble variance. So that's the noise. So this is the variance that's due to just internal atmospheric variability. And this gives us sort of a signal-to-noise ratio. And we can see that the signal-to-noise ratio plot agrees pretty well with the pattern we see in this convective versus non-convective Eastern Pacific events. So that's suggesting that this partitioning between convective and non-convective Eastern Pacific events is capturing a lot of the predictable variations in the El Nino signal in this model. So again, it's supporting the robustness of those results. Looking at some other composites, so this is 2-meter temperature and precipitation for the convective Eastern Pacific events. And then here's the non-convective Eastern Pacific events and the difference on the bottom. So you can see for temperature, the non-convective Eastern Pacific events tend to be colder over the eastern North America. Although a lot of these composite anomalies are not statistically significant, but I'll come back to that when I talk about subseasonal variability as well. And then here are the differences. Precipitation-wise, the convective Eastern Pacific events much wetter over southern North America, non-convective drier, and then you see the differences over here. Okay. So this study did not include the last two El Nino winters, so I thought I'd just look back at the 2014, 2015, 2015, 2016. So these are true independent samples as a way to sort of test these ideas. So you can see 2014, 2015, this was a cold winter over the eastern U.S. So this was the I think, the last cold winter we've had. Also, the winter when I came, I was in San Diego in November, and then December moved back to the East Coast, so that was kind of a rude awakening. And then 2015, 2016, it was basically warm over, very warm over virtually all of North America. So in terms of, so the 2014, 2015, if we classified it would be a non-convective Eastern Pacific event, whereas the 2015, 2016 would be a convective Eastern Pacific event. And in terms of temperature, you can see there are, I think, some notable similarities here. And again, 2015, 2016 was warm everywhere, but some of the regions of the enhanced warming, and actually Mexico was relatively cool, so cool in a relative sense. So there, I think, some of these differences that between these two winters are consistent with what we see in the composites. Precipitation-wise, you can see 2014, 2015 was much drier, particularly over the eastern U.S. And in terms of the composites, I think over the eastern U.S. there's pretty good correspondence. Over the southwestern U.S., not so much. So remember, this was very dry, and especially for this 2015, 2016 winter, it was a surprise that it was so dry over the southwestern U.S. And so that's a scientific question that's been that some have been trying to address, is why was it so dry? And all I can say is that the results I show here cannot explain it. So this is something that requires a different explanation, and there are some studies out there that are trying to address this right now. But overall, I'd say that these two independent samples, they don't. I wouldn't say they don't invalidate the results that I've shown so far. Yeah, I just also want to go back to the 2014, 2015 forecasts and the NOAA evaluation. So this was the temperature and precipitation pattern that verified. And this was the NOAA's mid-November forecast. And you can see, some areas did well, some areas not so well. But the forecast looked more like a canonical El Nino signal. But if they'd used the sort of the non-convective Eastern Pacific El Nino composite, I think overall they would have done even better. So it's suggesting that I think there is room for incorporating some of these other SST force variations into the seasonal outlook. So I guess there's hope that some of these variations could have been predictable on seasonal timescales. Okay. So as I've already discussed, one of the limitations with these small sample sizes is that we have limited robustness in the seasonal mean composites. And that means that a lot of these composite anomalies are not statistically significant, and that will also limit our confidence in how physically meaningful some of these results are. However, a lot of these important dynamical mechanisms for these teleconnection patterns are occurring on subseasonal timescales. So if we can focus on the subseasonal evolution of the OLR and the teleconnection patterns, we may be able to zoom in on times when this OLR signal is stronger, and we may be able to detect more robust features on this subseasonal timescale. So what I've done is I've started by looking at the subseasonal evolution of the OLR anomalies by projecting the 7-day running mean OLR anomaly onto the seasonal mean OLR composite fields for both the EPC and EPN events. So this gives us a time series of how well the 7-day running mean OLR essentially corresponds with either the EPC OLR composite or the EPN OLR composite. So after getting this time series, I identified its subseasonal events when this projection time series exceeds 1.5 standard deviations. And so we can look at the time series, the composite projection time series for these subseasonal events for both the convective Eastern Pacific and non-convective Eastern Pacific events. So this is looking at the composite projection time series from 20 days before peak to 20 days after peak. And so what we see for the convective Eastern Pacific events, the composite amplitude is high the whole time, so that these OLR anomalies are persistent. But there is some subseasonal growth and decay over the time scale of around 20 days. And for the non-convective Eastern Pacific events, the subseasonal growth and decay is even more dramatic. So you could see, fairly weak anomalies at minus 15 rising and then decaying again by 15 days later. So over a time span of about 30 days, we see substantial growth and decay. And looking at the composite OLR field, so this is 15 days before peak, and then 5 days before peak, you can see the anomalies are strengthening. And in the case of the convective Eastern Pacific events, they're also spreading eastward. This is lag 0, so this is the peak of these subseasonal events. So the peak amplitude as well as a peak eastward extension for the convective Eastern Pacific events, whereas more or less strengthening in place for the non-convective Eastern Pacific events. 5 days later, so the anomalies are starting to weaken. And then this is 15 days after peak. You can see still persisting for the convective Eastern Pacific events, but very weak for the non-convective Eastern Pacific events. Okay, so we could also look at the evolution of the 300 millibar heights on the subseasonal time scale. And I'm going to focus on the non-convective Eastern Pacific events because these are the ones that are most distinct from the canonical El Nino response, and they're also where we don't have a strong signal-to-noise ratio on the seasonal time scale. But this is 10 days before peak. You can see most of the anomalies are weak, except over the northwestern Pacific. We have this low over high dipole. Okay, so this is now the peak of the OLR anomalies. We see a distinct wave train pattern has developed. Negative anomalies have developed over northeastern North America. And this is 5 days later. The anomalies have strengthened. And then a lag about 10 days. So 10 days after the peak of the OLR response, we see the peak in the 300 millibar height response. So that's a 10-day lag, and that's, I think it agrees pretty well with theory, like Jin and Hoskins, 1995. And what we see is this well-defined PNA-like wave train. And one thing I want to point out is this pattern closely resembles the seasonal mean composite I showed earlier. But the seasonal mean composite, the anomalies are not, the composite's not statistically significant over a large area. However, it's much stronger and more significant on the subseasonal time scale. So what this is suggesting is that this pattern is in fact a physically robust pattern. It's just it doesn't persist typically throughout an entire season. So that's why the signal kind of gets washed out on the seasonal mean. But on the subseasonal time scale, it is clearly a robust pattern, and I think it increases our confidence that this is in fact a pattern that's forced by the tropical convection. So I think this is a case where zooming in on a subseasonal time scale can help us to increase our confidence in the robustness of these results. So this is 5 days later, the anomalies start to weaken. And then this is lag plus 20 days. You can see most of the anomalies have weakened, except over the Arctic, where positive anomalies are persisting. Okay. Then look at the same thing, except for now for temperature. So this is minus 10 days. Lag 0, you can see negative anomalies developing over eastern North America. 5 days, these anomalies have strengthened. And by lag plus 10 days, again, we see this the peak amplitude, so strongly negative anomalies over eastern North America, positive anomalies over Alaska. And again, this pattern closely resembles the pattern we see in the seasonal mean composite. So again, I think it's really supporting the robustness of these results and showing that on subseasonal time scale, we do see a very robust signal. So then this is 5 days later. Much of the anomalies are decaying. And then by lag plus 20 days, most of the anomalies are weak, except over the Arctic, we have positive anomalies persisting. Okay, so why do we see some of these differences? I just want to point out a couple of things. So first, looking at the variations in the storm track between the convective and non-convective Eastern Pacific events. So on the bottom panels here, I'm showing again SST and the OLR anomalies. In the top panels here, the colors are the root mean squared bandpass filtered 500 millibar stream function anomaly. So this is a measure of the strength of the storm track. And the contours are showing the zonal 200 millibar zonal wind. And one thing we notice is that for the convective Eastern Pacific events, where the convection extends farther east, we see a zonal extension of the upper tropospheric zonal wind, and as well as the storm track extending all the way into southern North America. So that's likely one reason why we see a much wetter southern North America for the convective eastern Pacific events, whereas we don't see that strong zonal extension of the storm track, where the convection is more confined to the west, and so that I think that's a big factor why the non-convective eastern Pacific events are much drier. Okay, and then here's looking at the difference again, the storm track as well as the zonal wind. And you can see the storm track differences are closely following the upper tropospheric zonal wind. I think that sort of correspondence is in good agreement with several previous studies. And one other thing I just wanted to focus on that I thought was interesting is differences in the Arctic temperature impacts. So one thing that it appears that the non-convective eastern Pacific events are associated with polar warming, whereas the convective eastern Pacific events tend to be associated with cooling over the Arctic. So this was, I thought, was an interesting contrast, as you can see clearly here. And this did seem consistent with the so-called the tropically excited Arctic warming or TEAM mechanism. So this is an idea led by Suk-Young Lee, and I was one of the co-authors on this paper describing the TEAM mechanism, where the idea is that positive convection anomalies confined to the Indo-Pacific warm pool can excite these poleward propagating orosity waves that warm the Arctic through three different ways: through enhanced poleward heat transport, adiabatic warming, and enhanced downward infrared radiation. And this idea relates to the constructive interference with the climatological stationary wave. So if we increase the zonal east-west contrast in tropical convection, we have a tendency to enhance the climatological stationary wave, which then warms the Arctic through these mechanisms here. And there does seem to be consistency here in that the non-convective eastern Pacific events are enhancing this east-west contrast in OLR, whereas the convective eastern Pacific events have a tendency to smooth out these gradients by putting convection where we normally don't have convection and decreasing convection in the warm pool region. So look a little bit more closely at this. So here I'm showing, just trying to illustrate how well or how poorly we see this constructive or destructive interference with the climatological stationary wave. So the bottom panel here, I'm showing again, the colors are the composite anomalies of the OLR, and the contours are the climatology of the OLR. And this is for convective eastern Pacific events. And then in the top panels here, the colors are so this is eddy 300 millibar stream function. The colors are the composite anomaly, and the contours are the climatological eddies. And so what we see for the convective eastern Pacific events, it's like what I said before. We tend to smooth out the east-west contrast in tropical convection. So we're putting convection where we normally don't see it, reducing convection where we normally have it. And there is evidence of this destructive interference with the stationary wave. So these negative anomalies corresponding with this the climatological positive eddies and positive anomalies where the eddy stream function is negative. Compared with the non-convective eastern Pacific events, it's a bit different here. Now we have a strengthening of the zonal east-west contrast, and at least a tendency to constructively interfere with the climatological stationary eddy. And I think this is clearest if we look at the difference. So again, looking at the difference between convective and non-convective, so we see again a weakening of this zonal contrast in the convection, and consistently we have a weakening of the climatological stationary eddy, and that can impact of course the poleward heat transport into the Arctic region. Okay, so this is the last slide I'm going to show. So this is just the idea that I haven't followed through on yet, but I just thought I thought it was interesting to consider what the implications for climate change might be. Okay, so what I'm showing here is that this is just another way sort of illustrating some of the ideas I talked about. So let's say we did a one-sided linear regression at 300 millibar height. So this is showing the Eastern Pacific relative SST on the x-axis. So that Eastern Pacific box that I showed earlier. And then this is the geopotential height at some grid box. And let's just regress the 300 millibar height on the Eastern Pacific relative SST, but let's only consider El Nino events. So those are these dots in red. Okay. And if we do that, the y-intercept here is going to be basically the 300 millibar composite for El Nino events, right? And the slope is going to really capture the difference between the convective and non-convective Eastern Pacific events, right? These events are going to be convective Eastern Pacific events. These events are non-convective Eastern Pacific events. So the slope is capturing the difference. If we look at these beta naught and beta 1 in observations, we could see that it agrees with the patterns I showed earlier. So this is very much like the composite 300 millibar height pattern I showed earlier, and this resembles the convective minus non-convective Eastern Pacific events. If we did the same calculation for CMIP-5 models, the contrasts aren't as stark, but there are differences here. So this is beta naught for models, and then beta 1. So you know of course there are reasons to believe that the models don't capture the teleconnections correctly in all ways. And if we consider, how the equatorial Pacific SSTs are projected to change under global warming, we see that there's a projection that the equatorial Eastern Pacific is projected to warm more than the tropical mean. So if the Eastern Pacific is warming more than the tropical mean, that means it's reducing this barrier to deep convection. And it should be easier to get these convective Eastern Pacific events relative to the non-convective Eastern Pacific events. So let's say that all I know is that this is how El Nino varies in the historical climate. And I don't know how El Nino is going to change, and I don't know how the relationship between convection and the atmosphere is going to change. But the one thing I do know is that how the climatological SSTs are going to change. So I would think that perhaps the El Nino teleconnection pattern is going to resemble this beta 1 term, because we're going to see more convective Eastern Pacific events relative to non-convective Eastern Pacific events just by this change alone. And if you look at how the 300 millibar heights projected, the El Nino 300 millibar heights that are projected to change, you could see there actually is a pretty decent resemblance between this beta 1 term and how the teleconnection is projected to change. So this suggests that just knowing how the El Nino teleconnection varies in the current climate and how the tropical mean SSTs are going to change can give you some indication of how the teleconnection might change under climate change. So that's just an idea that needs to be refined further, but just something that shows that there may be a connection to climate change here. Okay, so these are my conclusions. So basically, the nonlinear relationship between SST and atmospheric convection in the eastern equatorial Pacific is a fundamental element for the diversity of El Nino teleconnection patterns. The lack of robust teleconnection differences between the eastern Pacific and central Pacific El Nino over North America and observations may relate, in part, to the fact that some classified EP episodes are too weak to induce eastern Pacific convection anomalies, and some strong central Pacific episodes may still generate positive convection anomalies in the eastern Pacific. But the fundamental dynamics associated with El Nino teleconnection patterns occur on intraseasonal timescales, and so focusing on subseasonal rather than seasonal timescales may yield more robust El Nino impacts. And the largest EPC-EPN teleconnection pattern differences are found over northeastern North America, southern U.S., and northern Mexico in terms of precipitation, and the Arctic. Okay. Thank you very much.
Yes, very interesting talk. You have a lot of questions. I'll see you later on. So, the first question is that you showed that the model actually produced something much weaker than the observation. So, what's your sense? Well, is the model bad, or is the observation sort of noise?
Yeah.
Is contaminated by noise?
I think, yeah, that's kind of hard to address. I think it's potentially both. But I'd say, first of all, you can't really dismiss the contamination in observations, because there is going to be uncertainty there. But at the same time, the fact is this area is statistically significant. So, and here there's only a slight bit. So the fact that this is a large area that's statistically significant suggests that it's at least robust enough that we'd expect a high probability that this sign should be positive, and maybe it can maybe even make a stronger statement with the alternative test. Maybe I wouldn't be surprised if it's significantly stronger than whatever the anomaly is here. So I think it's probably both.
So have you looked at things like the CSM large ensemble or other
CSM.
The large ensemble has 30 or about 40 members, so it should.
Yeah, I did. In the paper I looked at several other models, and there were variations. So yeah, I think this may have been, the AM 2.1 may have been, I have to remember the details, but weaker than some of the other models. So there are variations, and so there definitely are model-to-model variations, and I think some that will get a stronger pattern. But then there are also, I think, anomalies showing up elsewhere too in the other models, and yeah, I have to look back at the details. But all I can say is that there are definitely variations in the models.
Very nice. When you do the subseasonal, do you use a bandpass filter to do the subseasonal response?
I mean, it's just 7-day running mean.
Oh, okay.
So that's basically it. Yeah.
Yeah, following up on the subseasonal part. So your subseasonal part, actually, you look at the OLR instead of. So is there a seasonal temperature signal? Because in your seasonal, you sort of basically propose that it's the relative SST that drives the OLR difference. But in subseasonal, it's probably just variation of the OLR. So is that predictable?
So I mean, I don't think, I mean, so predictable, I think it may be somewhat predictable on atmosphere, on subseasonal timescales related to the atmosphere and initial conditions, but I don't know if there's any additional SST related boundary or just boundary condition related predictability with that. So yeah, so I mean, I haven't looked at whether there's some sort of SST footprint. I wouldn't be surprised if there's some SST footprint of the atmosphere forcing the ocean, but I don't know if there's really anything more from the predictability perspective that we can get from the ocean without the the atmosphere for those timescales. Yeah.
So for the future climate, you show the Eastern Pacific warm more. Is this just from the GFDL model, or it's across the CMIP model?
It's pretty robust in the CMIP models. So that was what I showed. Was I think that was from a CMIP-5 ensemble mean. But there is debate about whether or not, since if you look at the historical record, the pattern of warming has not followed that pattern too well. So there is debate about how much we can trust this. So yeah, I'm pretty sure this was from, I took the average of a bunch of CMIP-5 models. So so this projection is robust, but I think there's still debate about how much we can trust it. But I guess the main point here is, even if this is wrong, it's saying, given this change, we could make some sort of prediction about how the teleconnection is going to change. Or if it's the opposite sign, we can make the opposite prediction. So given this, we can maybe have some idea.
One last question. So I think in the CP El Niño research, it is always difficult to find the mechanism of why the EPCP occurs. Did you find any mechanism of non-convective to convective? Why?
Well, I mean, so it's it's mostly an amplitude issue. So the mechanisms that lead to the amplification of El Nino, once they just cross that convective threshold, then you're inducing, you're able to get the convection to the Eastern Pacific. So it's just a matter of being able to raise the SSTs to that threshold where you can have positive CAPE. But there are ideas that there are also potentially feedbacks, and so how this convective threshold behavior also contributes to the diversity of ENSO itself. because once you get the the convection to the east, you're also going to impact the Archimedes feedback and things. So I think, like Ken Takahashi has done some work that shows how potentially this nonlinearity can be important for ENSO diversity itself. So I have to review that a little bit more. But yeah.
What is that like? Is it a physical threshold, or do you think it's a relative threshold? Meaning that in a future climate, the threshold for convection might be different.
Relative to the, it's certainly relative, but it holds pretty well relative to the tropical mean. So, it's going to closely follow the tropical mean changes in SST.
Okay, so let's keep our discussion during lunch, and students are encouraged to meet with the speaker after the lunch from 1:45. Let's thank our speaker.
Thank you very much.